In this video, we are going to add a FIFO to the cape for the BeagleV Fire so that it can capture high-speed input data such as might come from an analog to digital converter or other sensor and capture it into a buffer, a FIFO, and then you can read it out slowly over the APB bus and do whatever processing you need to on it. So I'm going to add it to, I was struggling between the Verilog playlist and the BeagleV Fire playlist, and I think it'll be mostly BeagleV Fire. So I'm going to put it into this list. If you're new to BeagleV Fire, it's not a terrible out of the box. It walks through getting everything going. If you can get this going, then you can get Gateware going in this video. And these two are probably the most important two videos for getting Gateware up and running. Yeah, so let's hit it. So probably what we'll do first is we'll do a demo on how to go through the whole build process. And then we will then do a dive into the Verilog code and then another dive into the C code. So let's see, where do we begin? Let's begin with openbeagle.org. My username bustedwing1 and my repo gateware serve on fire. This is a fork of the BeagleV Fire gateware, and I've just been throwing in features along the way in order to get it. So in this one, I've already done a build. They have an automated build process on the Beagle on these Beagle servers, and so basically when you push your design, it kicks off a build process. Um, and then you can monitor it with this pipeline, build pipeline, left click, and you can right here where it says passed, that means that latest build I had passed and it was successfully built. So all you have to do is go over and click on the load artifacts, left click, and then left click on build job archive. So you left click that, and you can see it's downloading to your downloads folder. And so then I go to Git Bash, so I'd recommend installing Git Bash. It's a really cool and easy to use program. It basically gives you Linux on Windows in a very light manner. So here I am in PWD. You can see, so I'm at my downloads folder. You can get to that with cd tilde slash downloads. Again, PWD, and in my downloads folder, do an ls. You can see that this artifacts just got there, so all you have to do is unzip it. It deflates. Then you CD down to bit streams. So this one here, gateware builds tester artifacts bitstream. Do an ls. You can see this design here. You SCP this design to your BeagleV, and so I don't remember history, pipe, grep, what's SCP. Okay, so this is what I do. So you can cut and paste this line, or if you're into nice history shortcuts, exclamation mark 500, which will run this SCP command right here. SCP-R for recursive, this directory. And yeah, I've got a little problem. I have not yet turned on my BeagleV Fire. So let's go to do that right now. Okay, so that'll just take a moment. While we're here, let's do a device manager. Let's see what COM port it comes on. All right, so it usually takes around a minute to boot and establish a COM port connection. Oh, actually, we don't even need the COM port because we are SCPing it. But when we get a COM port connection, we'll also have Ethernet connection going to the board. Um, if you do not know your Ethernet port address, though, so I think this might be even worthwhile. Yeah, so we're on COM 19. So let's bring up PuTTY. So this is a good. This is pretty much all I use PuTTY for now is to uh, find. So it came up with COM port 19. So that's a hint right there. So that's changes from system to system. 115.200. So I always set the speed to 115.200, and I open it, and now we got to log in. It gives you right here the username and password. So you just enter the use. That logs in. And oh yeah, even before I logged in, it gives you the answer to what you're looking for, in that they are on port 172.16.07. So that is the port for my system. For every system, I imagine that's going to be different. So 172.16.07. And so 172.16.07. So all you have to do is run, let me just type it out, scp-r for recursive dot slash my FPGA dot side. The username over on the BeagleV Fire is, yeah, it's Beagle, and oops, I think, what that? 172.16. So it's the IP address that's on your local network, colon, and you don't need to type in the home beagle, it'll automatically do that. All right. And so now you log into it and with the password, which is typed right above you, right here. And so this is dumping your the archive up to the BeagleV Fire, and now I tend to use I tend to prefer to do an SCP into uh, into it. So right here, I've gone back to my Ubuntu VirtualBox. It gives me a little bit better ride, I think, than the Git Bash. And then I do an SCP over, I mean, an SSH into that. So, SSH. All right. So here it is, SSH Beagle at 172.16.0.7. Again, that changes for your each network. And so that should get you over there. And then you just enter in the password, which is again written right there. All right, and now you're logged in, and then you do an LS, and you can see your custom FPGA design. And all you have to do now is you have to run it. And so now again, I never remember, but I'll get the command right here. History grep. This. All right. So this is the command that we're going to be using. So you have to sudo the command, and it's slash user share beagle board gateware change gateware.sh, and then space dot slash my custom FPGA design. All right, and then hit enter, and enter the password, which we all know and we've been entering over and over and over again. Okay, and there it is. It's running and it's building. And so this takes around a minute or two to do. So that is the second process. That's loading. Your BeagleBone will boot, and you should see some LEDs like on 5 and 6 blinking in a certain different type of like in a boring pattern. But that indicates that you successfully loaded and your new image from or my image up into your Beagle V Fire. And those are the main steps to cloning and loading it onto your Fire. It's very straightforward. You can see right now my connection is closed down. And oops, it's even Putty is closed down because we're in the middle of rebooting. And when it comes back, um, we should be able to actually run some code. So let's pull up the device manager and we'll know it rebooted when you start getting a COM port that comes back. So that's the process to get that going. I think the next step will be a quick little code review of of the actually the ADC FIFO. It's a pretty straight block, straightforward block. The cape, which instantiates the FIFO. The tickle file, which lets the build process know that we are including this FIFO in the design. And then we'll take a look at adcfifo.c, which is a little very primitive, minimal piece of code that uses the FIFO. So let's get this all set up here. Oops, what did I do? Silly me. Need the full path, of course. Get the cape, get the tickle, get the ABC. All right. So here we are in, nope, we want to start with the FIFO. And so in the FIFO, it's very primitive design, not too robust, but good enough to do what we need. You got clocks and resets, which are standard to almost every block. We have the APB interface, which we've talked about in other videos. We've got an iData, which is coming essentially from your sensor. And we have an iData V, which is says that the data is valid and that it should be written into the FIFO. Um, so we've got some register definitions to make, and this one here is the big one. It's mem. Uh, so it's this one. This line here makes a 512 entry by 32 memory that the FIFO will be using. We have a write address, which gets incremented whenever data is written into the FIFO and wraps when it gets to 512. And we have a read address bus that every time the data is read from the FIFO, it increments, and then it wraps when it gets to 512, wraps back to 0. We have a little controlled status register that the lower 16 bits provide the count of the number of values in the FIFO, and the upper, like I think bit 16 like resets or enables this FIFO. And then we got a select FIFO, which is where we have, if the P cell comes in from the APB bus saying this block is selected, we look at the bit 2. If it's a 0, then we're selecting the FIFO. And if we're having a 1, we're selecting the control status register. I'm thinking of swapping these two, but right now that's where it's at. We also have a couple little wires that when the FIFO is, when the count equals 512, we're saying it's full. When the count is 0, we say it's empty. Um, right here, this FIFO reset, that's the reset bit 16. So if the processor writes bit 16 to a 1, it'll clear the FIFO. And then so you can reset it, and then enable it, and then it'll capture the next 512 samples, and then it'll lock up when it gets full. And then you can read out the 512 samples. We have a memory write so that whenever the data is coming in and you're not full, you can write, it'll write to the memory. We have an increment write memory, which is just a renaming of the memory write. We have a memory read, so whenever the piece cell from the APB bus is asserted and we're not writing, and we have the and the cell and the address is selecting the FIFO, and something, and the FIFO is not empty, then you can read. And the address increments whenever we do a read, and the P enable is asserted. And that P enable is like a 1 clock tick pulse. That allows us to increment the, the read address. The memory cell is very simple. This is called an inferred memory, which means that the synthesis tool will turn this into an actual block RAM, like using the PolarFire's LS RAM. So if there's a memwrite, then whatever's on the iData bus is going to get written into is going to get written into the memory at this address, which is incrementing after every read. We'll see it just down a little bit below. If we're selecting a FIFO, then whatever's on the address, but whatever's on the memory at this read address location will be put onto the read data bus of the APP, which will then get to the processor. If we're selecting the CSR, then whatever is in the CSR will then, which is usually like the important thing you want there is the count. That count will then get sent onto the read data bus of the APB, which will then get to the processor. If nothing's being selected, then we're driving a 0 onto the PR and onto the read data bus. Here is some logic where most of this is controlling the P ready and the CSR, the control status register. So we start off with P ready 0, and then whenever P cell is high and it's not P enable, then we're going to assert P ready. So P ready will go out for like a 1 clock cycle pulse. Let's see. With CSR, we started off with bit 16 as a 1, meaning the FIFO is in reset. And then to start it, you take it out of reset and you drive this whole bus to 0. And then by just reading this bus, the count will be placed on the lower 15 bits of the CS ready. And so you can read back the count of how many entries have data in the FIFO. And here we go on the last piece of the code review here, is that we've got the read and write we reset the read address, write address, and count. And then whenever we're incrementing the read, we just increment it. Whenever we're incrementing the write, we increment it. And as far as the count's going, it's kind of cool. Is that whenever we're incrementing and we're not reading, then the count's going to go up by 1. Whenever we're incrementing and we're not, whenever we're reading and we're not writing, then we're going to decrement. And so like if you're doing a read and a write at the same time, the count would stay the same. If you're doing nothing, then the count would stay the same. So yeah, so that's the code for this block. Let's close this out. Let's take a look at the cape. Control F, APB, ADC. All right, so here we've created a wire called ADC read data. Um, so we created this wire here. It's a 32-bit value, and so this value is going to be coming out of so let's roll back up to that one in a second. So here we're instantiating the ADC FIFO, where the first word in this line is the module name, and then the second word is the instance reference or instance ID. So this guy has to be unique. And here are all the signals, where these are the signals of the module internally, and in parentheses are the signals externally in the cape. Um, so, so right here, we've got read data. Internally, it's PR data, and we're going to put it into this wire APB ADC FIFO read R data, which we defined right here. Similarly, we have this select APB ADC FIFO, which takes, and if the P select is ever asserted, and the address is a 3, then we're going to assert this signal, and that's going to go into P cell. So this guy gets its own very own customized P cell. And so with those then coming out of the data, since all the blocks like Blinky and the RAM all drive 0 when they're not selected, similarly ADC FIFO drives 0 when it's not asserted. But if anyone is enabled, then that is the only one who'll get out, because he's the only one who's not zeros, and that will get onto the APB bus and squirt on over to the processor. All right, so that's this block. Control W. Now we're into the add cape tickle file, and so all you have to do is let it know that to include the APB ADC FIFO by adding this line. Yeah, that's it. And then we get to the ADC FIFO read code. And so this one, I don't actually believe we have any arguments. This is a file that I've just been modifying as I go along from one project to the next. But so I set the base address at 4103.000.000, and I said the block size is 20. And then which is, I think, the number of bytes that are available. I probably glossed over it, but whenever you're reading the FIFO, you're always reading like for this address 4103.000.000. So that'll pop a value off the FIFO. Then you read that location again, and you'll get the next value in the FIFO. So you don't have to increment the address bus. And let's see. So this goes into here, a little print statement. Okay, this is the most important line in this. That's kind of tricky. Is that this setup IO routine, which we'll jump down to in just a moment. You pass it in the block base, which is 4103.000, and the block size, which is 20. It can be a much larger number, like 4096, or even way bigger. And so this sets up a pointer, which is kind of like a virtual pointer that to the physical address of this. And so this is Linux's tricksy way of allowing you to get to this actual address, physical address. So you've got this address here, and then some people might use like pointer math and things like that. I just use it as a big array of, like, the first location is the CSR, and so this line here actually reads the CSR. So the value here is returned and put into this local variable CSR, and if CSR does not equal that, then I write a little error message saying that the ADC is not reset, and it should be. All right, and then I go in and I say, okay, this is where we're writing to that CSR. So we're writing a 0 to that first location, which is the CSR, and that should make that reset bit go low. And I'm surprised I didn't have another check to see that it went low, but it went low. And that deasserts it. Then I wait a certain amount of time for the FIFO to fill up. And then I go in, and we could have polled here, and I'll probably enhance this so that it polls the count register until it gets full. But right now I'm just going to wait. This polling loop just delays for a while. And then I go in and I read the count from this register. I read the count value, and the count is blah. It should be greater than 0. It's almost always going to be 512, which is 100. Right? No, 200, I think. Whatever. It's going to be always full. Yeah, and then we're going to unmap when we're done with the program, where you just unmap the block base, and that's it. to dive into the setup IO function, you kind of open a file, this dev mem. Everything in Linux is a file. So you open that, you get a file descriptor. If it failed, I exit. If it and then I run this, and this is the Linux function that maps the hardware base address, which is coming as the argument of like 410300, and it maps the size, and it gets that blocks out that memory region, and it sends you a pointer to it, a virtual pointer, then you just close the file and you return that back. And so that's basically it for how to actually run it. Control W. I mean, that program works. And then let's see. Let's keep blasting along. Um, Now I believe that uh, uh, the boot process is finished. So we should be able to, you can see that this got closed during the boot process. So let's just SSH back into it. I'm here and temp pwd and oops, and ls. And so here's what we have. This is over on this is on the BeagleV Fire. So I'm SSH'd into that BeagleV Fire. And so we have these little programs, and so we should be able to run it. So you always have to sudo when you run it. I need a dot in front of things that I'm using, here, this first. Let's run it first. Sudo / adcfifo. I think that's it. All right. And so if you can see, this goes from 87, 88, 89, A8, and oh, I didn't. Let's go back. Where are we? Let's go there. Let's go to the Cape. Hold on one second. Hold on. Just hold on. All right. So things that I added to this design as well that I totally blasted over is that I added in this little block here, which is kind of like an ADC emulator. Generates incrementing pattern. So what it does is it has a count, it just bumps that count, boom, 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 boom. So every clock cycle, it's going to increment that count, which basically, and it has the data valid asserted, which basically means that this guy is going to be writing a piece of data every clock cycle. So I think on this, the cape is running at 50 megahertz. So this is a data sample getting sampled at 50 megahertz. This whole design, I think, could easily probably run at 100 or 200 megahertz. So that's how we're getting the data, and it's just an incrementing pattern. And so now if you look into this, it's just that counter was going up, so 32-bit counter, and just it's incrementing through this little range. And I'm just reading, I didn't read all of the 512 values that were in it, but it gives you the flavor that it's working. All right, so what else? What else? What else? What else? Anything else worth mentioning? So we went through the build process. We went through all the code. We showed how to run the C program. I think that's it. That's all. Thanks. Bye. Oops.